there is a question in chat like, can we use medical images and all that? Yes, you can use it, but as I said, these images are super like a domain specific images, so you have to take care of a pre-processing of that, and there are some embedding models, specially designed embedding models to take care of such images. For example, uh, derm foundation model, it's an open source model used to take care of a dermatology images and all that. So if you want to work with an MRI images, CT images, you have to come up with a dedicated embedding model for such data. Okay, and there are some. Yeah. So okay. Yeah. So if there are no more questions, probably we can take a short break, and we will resume in maybe in next 10 minutes. Is that okay?
Yes, sir.
Yes, sir, it's okay.
So I'm sharing my screen. This is the clock going on for 10 minutes. So see you in 10 minutes. And we'll start with the part two of
Okay,
the
sir.
lecture. Thank you.
Thank you, sir.
Yes, sir. Good evening, sir.
Good evening.
Okay, for this session, I will be the host. My name is Nestor Phillips from ENTC department. And first of all, thank you, sir, for the advanced session. It was a very wonderful session. I got to know more insights about it. For the next session will be LLM Fine Training. I would like Mr. Bhushan, sir, to continue his session.
Thank you so much. Let me share my screen again and just give me a feedback if you're able to see it.
Yes, sir.
I'm going in a slideshow mode. Are you able to see my screen?
Yes, sir, it's
Yes,
visible.
sir.
Thank you so much. So welcome back to the part two of the today's session, and today we will be discussing about LLM fine tuning. In our part one, we finished RAG, and when we did RAG, there are places where we discuss, like if you do everything good, there are still some places you will feel that, hey, because my embedding model is not good, my results are not good, or my final LLM is not good, which is not producing good answer, even if I'm giving a context well. And this should be your last option of saying that, okay, let me fine tune my LLM for my own domain or for my own task. So today, for next 1.5 hours, we will be discussing about what is LLM fine tuning, how it is done, what are the consequences, what care you need to take care. So, disclaimer, as we discussed, all views expressed in this presentations are my own. These are my personal opinions and do not represent my employer's view by any way. So, developing an LLM. So, imagine we all are very ambitious and we think of developing our own LLM sitting in the classroom. So if you want to develop your own LLM, it has three uh, parts of it, or three stages of the development. Stage one is called as an building an LLM. Stage two is called as an pre-training, and stage three is called as a fine-tuning. So today's topic is LLM fine-tuning. Okay, so if you see that this is the step number 8 in this pipeline. So because we have diverse audience in this lecture, I'll make sure that we will give some background, and so that this point number 8 will be well received, and I'll make sure that all the nomenclatures and the terms are clear when we come to the point number 8. So I'll spend some 5 minutes on stage one, like what do you mean by building the stage? What do you mean by pre-training of LLM? And then we'll spend good amount of time on LLM fine-tuning stuff. Hope that is okay. So let's focus on this first aspect, building an LLM. I am not even started the training. I'll first spend some time on deciding, data preparation, that what data I should use for building one LLM, what attention mechanism I should be using, what is my LLM architecture. So, at this stage, everything is on a paper. I have not even started the training job. So that's what this is a, planning stage, building an LLM on paper. And then a pre-training stage is done where you get the foundation model out. So let's understand the stage number 1+. So what are the prerequisites of this lecture? Okay, attention is all you need. Okay, and this is the, I would say, the mother of all the papers and all the innovations that we are seeing in this large language domain. So though I call this as a prerequisite, I understand that it's not something that's very uh, trivial or intuitive to understand all that stuff. So I just spent some time on this architecture, to bring everybody on a comfortable stage to understand the further terminology that I'm going to use on this session. So this architecture may look very complex in the beginning, but in a very simplistic manner, this architecture has clear two parts. The first part is called as an encoder, and second part is called as a decoder. So let's understand what it is. Suppose you want to do a translation task. Okay, and the input that is given to you is called, this is an example, this is an input text, there are some pre-processing steps done, and eventually you get some embeddings out of it. Okay, so if you remember, like the paper, the 2013 paper that we discussed, it's called as an Word 2 vec paper, right? Word 2 vec. So it was a, a path breaking paper at that time, which actually unblocked people, using neural networks for a text kind of a data, because this paper was actually converting text into a vector form. Okay, so it was converting words into vectors, and those vectors, then immediately after Word 2vec in 2023, you will see that 2014 there was a paper on RNNs, and then after 2044 RNNs was a hit. There was some issues, and then you see LSTM and those kind of publications coming out. But the biggest blocker was, how can someone convert text into vectors? There are two issues. Okay, and apart from vanishing gradient movements and everything that you learned in the theory, there were still two issues in this. Okay, one of the biggest problem in these architectures, why the results were not good or why the training time was really long, the first issue is called as the embeddings, the vector representations that you get from that 2023 paper, let it be Word 2vec or Glow, those are called as an non-contextual embedding. Those are called as non-contextual embeddings. Okay, now let me explain what do you mean by this non-contextual embedding. Suppose I'm using a sentence like, I am going to the bank. I'm going to the bank to open an account. So word bank came. And I can say that I'm writing a poem on the bank of the river. On the bank of the river. One of the limitations of these 2020 or 2013 Word 2vec and Glow is like it's a Word 2 word represent. Eventually, you will have a one vector representation of this word called bank, right? And that's why it's called as a non-contextual, and it is not taking consider the surrounding words about it right now. Like, I'm going in a bank to open an account. I am writing a poem on the bank of the river, right? So those are non-contextual embeddings. So in this, you must have heard a paper called BERT, and as the name suggests, or BERT, which is as a bidirectional encoder representation of a transform. Means what? Encoder representation of a transform, only the left hand side of the transformer, and a bidirectional, right? So what they have done in a very simplest way is, suppose this is your word 1, this is your word 1, this is your word 2, and this is your word 3. Okay, W1, W2, W3 are the word 1, word 2, and word 3, and these are your non-contextual embeddings, coming from your word 2vec or some other thing. What they have added is another box here. This box is called as an attention blocks. I'm talking to you as an 100 feet level explanation. Attend some neural network, some trainable parameters. And this word 1, word 2, and word 3 are passed together to this box. And it will give you a new representation for word 1, called it as x1. And similarly, there is another box here, another box, attention block, or you can say that self attention block. And all those vectors are connected here to get x2. Now these boxes are actually trainable components. I'll not go deep into this. But what you have learned is, so this W1 was an original word. This is the non-contextual representation, say word 2vec representation of it. So from here to here, what you have done is you have done conversion from non-contextual embedding to now a contextual embedding, because this x, when you create this x1 vector, it has a contribution from this w1 also, w2 also, and w3 also. So now if you get a vector representation, it is coming from the surrounding words as well. So the new encoding or new embedding that you get at the end of this are non-contextual, are contextual embeddings now. Okay, this is one. Second advantage is, if you see this block and this block can execute in parallel. One of the limitations of RNNs and all that is, if you remember that neural network architecture of an RNN, it was something like this. You used to give an input. So you used to give you one word at a time. This was your one word at a time t is equal to t0. And then you generate an outcome. This outcome you gave as a feedback, and then you apply next word. So if you see that RNN architecture, LSTM architecture and all that, you were ingesting one word at a time. And that one word were coming from some previous layers and all that, right? So it was a sequential program, kind of an stuff like one word and all that. Where if you see this kind of an architecture, you will see that all those words can be applied together in a one go, because these blocks are independent of each other, and that processing can happen parallelly, right? So what you have learned from this background theory is that this is an so the if this is the word, everything can be processed in parallel, and eventually you get a vector out of it. That's the biggest advantage I see from this application. Okay, these embeddings are now contextual embeddings, and this processing happens entirely together in a one go, and then you get the embeddings coming out. However, this decoder is still, one word at a time. So from here you get an input embeddings, and you generate an output like in one word at a time. So that isn't, so that the newly generated word is coming out. So I'll just uh, share the screen again. So now, if you use some of an LLMs, you will see that, and in their API there is a mode where you can actually produce the outcomes. So if you give some input, that input is given directly in a one go as an input, but this output of those LLM is still one word at a time. So this will produce a one word. That one word also goes back along with the previous input context, and then you predict next word, next word, next word, next word, next word, till the time you get end of statement or end of this. So this cycle is given. So this decoder output is still one word at a time, but at least at an encoder side, you give a sentence, you directly get an embedding coming out of this. Okay, so that's a background. So if you just take an encoder part of a transform, and then it becomes bird. If you just take a decoder part of it, then it becomes a GPT architecture and all that stuff. Let's move further. So suppose you decide, I'll collect my training data, I'll choose what kind of an architecture I want to use and all that. Now then comes the stage number two, and this stage two is called as a pre-training stage, where you actually run the training job. You evaluate your model, and you actually load your train model weights and all that. This is a core part of it. This process is called as a pre-training. But it's very important for you to understand what happens in this pre-training phase before you even think of fine-tuning your LLM and all that. So let me explain you this stage two called pre-training stage. So if you go and download this Llama 2 model, which is 70 billion model. So if you go to your website and actually download that, you will get a package, and that package has two files. File number one is a parameter file, which has a weights of those models. So It is a 70 billion model. So 70 billion numbers that you are saving. So you need like a 140 GB of a space to save those 70 billion numbers. That's your parameter file. And then you get a C file called run.c. So this C file just, very optimized C code, just under 5 lines of a code. In the first few lines, you can see that the code written to fetch the model weights locally, and then you get this model back. And then some lines of a code which defines the neural network architecture, and those weights are loaded to it. There is a way for you to give an input and the way to generate an output for you. So this is how the package, a foundation model, a pre-trained model that you get if you download any open source model. Okay. Now, because Llama 2 is an open source model, they have clearly disclosed, how they perform this training job. So based on their documentation, what I learned is something like this. What they have explained is they took the chunk of an internet data. Okay, and this chunk of an internet data, how much is like close to 10 terabytes of the internet data is taken by them, and they ran a cluster of GPUs, like 6,000 GPUs for 12 days to come up with those trained parameters of 140 GB. Okay, now you will imagine the kind of an compute that is required, and why creating those foundation model uh, is very expensive. This is what you are getting from this. The first question that came to my mind when I saw this documentation, like for this 10 terabyte of a data, and if you want to do some kind of a training, who will annotate uh, this data? So it's very important to understand nobody actually perform annotations on such a humongous data, and that's the beauty of an invention that we have done. So there is a term called self-supervised learning. Self-supervised learning, or in our LLM fine tuning, we gonna use this term called mask language training. Okay, let's understand this. What do you mean by self-supervised learning, right? So on this internet data, imagine you have a lot of textual data. What you do is, this is your word 1, this is your word 2, this is your word 3, and this is your word 4. Because the internet data is, you have downloaded this internet data, what you do is, this word 4, you hide it from your model, keep it with yourself. Only provide one word, one w1, w2, and w3 to LLM, and ask LLM. So this LLM is not trained for now, and ask LLM to predict the W4 dash. Now this W4 is a prediction done by LLM. And because this text is available with you, you know what should be the actual W4. So this W4 dash is prediction by LLM, and W4 is a ground truth. You can calculate the cost of W4 minus W4 dash, how many times you got them correct, how many times you got it, summation from 1 to say capital N, where this capital N is total mask word in your corpus. And obviously you go back, you change your word. So this process goes on and on and on and on. So this is called as a mask language modeling. Okay, and that's why they need so many GPUs and keep it running for 12 days, in order to keep training and all that, right? So what they achieved is, eventually, a language model pre-training means what? You are actually teaching your large language model to predict the next word. So when this LLM is not trained, you pass the word like the sun is in the, because this LLM is not trained, it makes prediction the sun is in the bed, which obviously incorrect, because you know what is an internet data that you have downloaded, right? So you repeat this millions of time, you update the model weights, keep doing this process till LLM is not learning to predict the next word. When you repeat it for millions of time, eventually you will say that the sun is in the sky, and you know the next word is a sky, and your LLM is also now learned to make prediction of a next word, and not for one sentence, for all sentence in a training data of size 10 terabytes of a text. And that's why such a huge compute is required. But eventually the task that you want to achieve is something like this, like the sun is in the sky. And that's why people say that LLMs are fancy autocomplete. So at this stage, and that's why this process is called as a pre-training. So LLM has just understood the English language, how it goes, like from previous few words, it is able to make a prediction about what should be the next word. Okay, now you will understand, is this kind of an large language model is really helpful for you to do any kind of an task, like the kind of an open model that you try today. They are not like that, they are not next word predictor, but this is the first stage. Okay, so because before you do any kind of an um, fine tuning and all that, you have to undergo this process. Okay, and that's why this process is called as an creation of this foundation model. So this foundation model, on such a test, what I would recommend is don't try from zero. Don't try to create your own foundation model. Rather, you start your, stand on somebody else's shoulder and make a longer jump. So that's how you start with a foundation model. And on the top of that foundation model, you perform the further task that you have to do. So from here onwards, the real lecture of LLM fine tuning will be started. So if you see my diagram, like LLM tuning flow is something like this. Lots of text data. We just gave an example of Llama 2 model, like 10 terabytes of text data from where you need to start. Mask language task, I already discussed you what do you mean by mask language task. And you get the base model. So this base model is called as a pre-training phase. At this time, your LLM is just a next word predictor. It's just a next word predictor, nothing else. And it is not useful for you to do any useful task at this time, because it's just a next word predictor. So after pre-training is done, the next step that comes into this flow is called as an instruction tuning. Okay, this instruction tuning is performed on highly curated data set, and that data set on a real world task. What do you mean by real world task? Real world task means text summarization, text classification, question answering, natural language understanding. These are called as a real world task. So on a pre-trained LLM, the next process that we do is called as an instruction tuning. Now let me help you to understand how this instruction tuning is done, and then we'll discuss. So instruction tuning, and it is done on, just remember, on highly curated data sets. Okay, so when this first term got tossed, so there was a publication from Google Research on 2022 in an ICLR conference. And in their paper, they say that fine-tuned large language models are zero-shot learners. That was the heading of their paper. They are called as a zero-shot learners. And this paper explores a simple method of improving the zero-shot learning capabilities of language model. We show that instruction tuning on a collection of data set substantially improves the zero shot performance on unseen tasks. This is a very important word, and I'm going to break this definition into small pieces to make sure that you understand what is going on. So they are proposing a new technique called instruction tuning, and they are claiming that it improves the zero shot learning capabilities of large zero shot. Let's understand this word. What do you mean by zero shot? Zero shot means this is an LLM, and you ask a query, and you don't give any sample examples. You directly gave a query and expect LLM to give you the answer. This is called as a zero shot learning. Instead of that, there is a concept called few shot learning. So in a few shot learning, you give the query, but along with the query, you give the pair of question. If the question is like this, my expected answer is like this. So you give a pair of question answer examples along with your query. That is called as a few shot learning. So what they are claiming is, we are proposing a new technique called instruction tuning, and this instruction tuning improves zero shot learning capabilities on unseen task. Means what? Some of the tasks which are not seen by the model, but it still improves their zero shot performing. It is a really, really big claim. Okay. And in their paper, the instruction tune model they gave a name to as a FLAN, fine tune language, FLAN. Okay. So remember this fancy name, and because it's an older paper in 2022, they use some that time the Google has a model called T5 model. Okay, so they consider this T5 model, and on this T5 model they perform the process of instruction tuning, and they got a new model called FLAN. Okay, and I'll explain you how this instruction tuning is done. Just get familiar with these words. So this was a base LLM, instruction tuning is a process, and the FLAN is an instruction tuned model. And they claim that this instruction tuning helps to improve the zero shot learning capabilities on the unseen task. So let's see what they did. If you remember, this instruction tuning is done on the highly curated data sets. So if you read their paper carefully, they said that we took 62 publicly available data sets. 62 publicly available data set, which includes some translation data set, some summarization data set, some sentiment analysis data set, natural language inference data set. So they took those all public available data sets and manually curated the inference data set. Now imagine the kind of an efforts that are put into this. So they manually created, and that's why it's a highly curated data set in order to question, if the input is given this and expectation is this, they actually created a target out of it and bring it to a supervised learning format, from this. The beauty is that this manually curated data set is also afterwards now open sourced for the researchers to try out some experiments. Let's understand what they do. And here please be very careful, because there was one word that was used, and that one word is called as a unseen task. So what they say is they started with a pre-trained LLM. Now pre-trained LLM is just the one who is a next word prediction, which is trained on mask language modeling, the first step. At this step, the model is just able to predict the next word. Okay, they took this pre-trained LLM, they perform this supervised tuning or instruction to highly curated training data set on the task B, C, and D. So B, C, and D, the task B could be summarization, class C could be natural language inference, class D could be Q&A. They performed training, but they took inference, like they tested on task A. Task A could be, say, summarization task. And that's what their claim is. When instruction tuning is performed on task B, C, and D, we observe that zero shot performance on unseen task is also improved. That's what their claim is all about. Okay. In their paper, they after like in 1 year, they did some extensive, again coming from Google research, they did some extensive testing on the claims that made in a previous paper and then published their results. And these findings are really, really important. So let me explain you the color of this, and then we can discuss all this stuff. So T5 is a model. Okay, this is a base model, you know or you can say the pre-trained model. Instruction tuning is not done. and directly fine tuning is done, which I am yet to teach you how to do fine tuning. So from T5 to fine tuning without doing any instruction tuning, this is represented by blue color. This is represented by blue color. Okay. And when T5 is done and instruction tuning is done, then you get flan model. And fine tuning is also not done. You just did instruction tuning. That is represented by this peach color. And you can see that there are many occurrences where you see that, oh, it performs amazingly well on on a compared to the blue curves. Compared to the blue curve, peach is still, what it is like. Try to understand this. What is saying that I have not done fine tuning on my task. I just did instruction tuning, and I saw that, like, if you get pre-trained model and fine tuning without instruction tuning, and then if you do just instruction tuning and no fine tuning is done, that is represented by this peach color. And the last graph that you are saying is you took the T5 model, the pre-trained model, you perform instruction tuning, so you got flan, and on that flan you further perform fine tuning, and that is represented by your pink graph. And all the different data set, you will never see an occurrence where pink is lesser than blue. You will never see the pink is, it could be same as blue, but in many other cases you will never see that pink is less than blue. Pink is less blue, never seen. Rather, in some cases you will see that even peach is greater than blue. Okay, so what is my conclusion from this is, instruction tuning always helps. You will never see that because I perform instruction tuning my accuracy goes down. Rather, they claim that even on unseen task, the zero shot capabilities are improving. So before you do fine tuning, doing instruction tuning is advisable, is what we learned from this 2023 paper. So if I come to this paper, like, lots of an internet data on say 10 terabytes of data, you download this pre-trained model. On the top of it, you perform this. Now this highly curated data is also open source, so you perform instruction tuning. Now when I say you, ideally not you people, now you can say that instead of baseline model, people are also releasing instruction tuned model for you also. So it is always recommended to get started at this step called instruction tuned dataset. Now, if you are doing your PhD research, if you're doing something very specific to the domain, as few of the example gave me, like in medical imaging or Sanskrit or some other language, other domain, where you feel that there's lots of internet data, there is no chance that the kind of a data that I'm working on, right? So you start after instruction tuning, then you can perform a similar mask language task on the top of this instruction tuned model, and then you get an enhanced model. Okay, so this is an optional step. I'm not saying that this step is must, but if you are working on some domain specific stuff, it is advisable to do this. And now this is an exact step where you will come. It's called as a prompt tuning, and this is a tunable part on personal style. So this is enhanced instruction tuned model, and this is an exact step where you will start performing the fine tuning of this LLM. So get the pre-trained model, make sure that it is instruction tuned. If domain is not very special, you come here. If domain is super special, then perform this step also. And now this is a tab, it is called as a prompt tuning. So now we are coming on a fine tuning step of this LLM, and let's understand why this particular step is kind of a trickier one. Okay, so fine tuning types. So first step is called as a supervised fine tuning. Second step is called as a reinforcement learning with human feedback, and third step is called as a distill, step by step. We have some restrictions on a time. I'll just see like how much we can explain, but at least point one and two definitely I will try to cover, and if time permits, we can cover the step three as well. So let's understand one by one. Okay. So what do you mean by supervised fine-tuning? And this supervised fine-tuning is exactly similar what we learned in machine learning, supervised learning. Okay, right answers are given and we need to provide more right answers, right? So large generic corpus pre-training is done. You get a pre-trained large language model. You people will perform instruction tuning on the top of it, and now this is a supervised fine tuning step where you get an annotated task. So as you mentioned, you need some training data because this is supervised fine tuning, right answers must be given. So annotated data has to be given, and then you get a task adapted model. Task adapted means performing summarization, performing classification, generating a text in particular style that you want. This is all dependent on how you are creating an annotated data set. So this annotated data set should have a input output format, like given this as a text as an input, I need this as an output. Create the pair of input outputs, perform this supervised fine tuning, and get a task adapted model of your choice. I think most of the audience in the today's class are very much eager to understand how can we get our task adapted model. I'm working on a problem called summarization. I'm working on a problem of text classification. I want to generate a text in a particular style. Then this is a step for you, like how can you do it. Now there is no term as in full fine tuning. There is some abuse of notation here, but I deliberately call it as in full fine tuning to make sure that everybody understands that nobody does this. Okay, full fine tuning means involves retraining of an entire LLM architecture. So in terms of a Llama 2 model, all 70 billion parameters you want to change. Okay, it means you want to change an entire LLM model suitable for tasks where high accuracy is crucial. Imagine, unless you are not working on some application where you are saying that no, not a single train weight is acceptable, I want to train it from scratch and all that stuff. Now I'm telling you this is not possible because you need humongous amount of a data. As I gave an example of 10 billion or 10 terabytes of a data, you can't get it. The training all the layers of LLM is costly and resource incentive. I don't know, you know as an individual can we even afford to keep that running for 16 days with a GPU cluster of 6000 GPUs and all that configuration. So probably this is not a choice for us. Okay, let's accept this. Now if we are not able to do full fine tuning, what are the options that we have? So that's why this is a very good research problem, right? At one side I don't want to compromise on accuracy, on other side I'm not able to, I don't have that much compute, I don't have that much cost, I don't have that much time, I don't have that much data. So that's why this is an amazing, like I don't want to compromise on accuracy, but I can't give you I can't give you that much compute, I can't give you that much time, I can't give you that much data, I can't give you that much money, but still I want to achieve an accuracy. Isn't it great? That's a good research problem. So let's see what hack people do. So the hack that people do, it's called as an parameter efficient fine tuning. Parameter efficient fine tuning. The goal is, instead of 70 billion parameters, instead of training 70 billion parameters, I can achieve similar accuracy by some fraction, some small percentage of those parameters, and I'll still give you the equal accuracy, by which I can save cost, I can save compute, I can save time, I can get less data, I can save money, all that stuff. So, what are the different PEFT techniques that are available today? Disclaimer: these slides are like a few days old. By the time I'm teaching you these slides, there could be steps number 5, 6, 7. I don't know. It's an evolving field. So I'm really sorry if I'm not discussing those, but these are the very popular PEFT techniques. The first one is called as an model level model level PEFT. Model level means what? You actually play with an architecture of this model. Okay, you change the model architecture. It is called as an adapter tuning, and I'm going to have a deep dive into it, like how adapter tuning is done. If you were attending, do you remember in our part one of this session where when we were doing RAG, there we came across embedding model, and I use this word of adapter tuning there. Okay, this is the time to have some deep dive. Second way of doing it as a feature level. So you actually do prompt tuning. Okay, you change the prompt, and rather you learn the right prompt for that. The third way is called as an parameter level change. So you actually, you don't add new architecture, but you play with the weights of the model, either theta or w. And then last is called as a partial fine tuning. This partial fine tuning is exactly similar to what you used to do in a deep learning, right? If you remember the concept of transfer learning, this is entire your architecture. You keep all these layers frozen, and keep only last few layers as a tunable layers, and by which way you do a partial fine tuning. Okay, only few layers, and then you get an accuracy. So this partial fine tuning I'm not going to teach. It's very similar to what we used to do in deep learning. But this point number 1, 2, and 3 is what I'll get, because these are new. Okay, these are actually coming along the way we are doing within large language models. So let's start with our first technique called adapter tuning. Adapter tuning is a PEFT technique. Okay, PEFT stands for parameter efficient fine tuning. Okay, and here you actually, this method is actually at a model level. So you play with an architecture of your model. Okay, how you do it? How you do it? So imagine this is your transformer architecture. So this is your multi-headed attention we discussed in the beginning. Then there is a feed forward, and this is your normalization layer. Here you add a new section. Here you add some new part in your model. Okay, and that is called as an adapter layer. So the zoom version of this particular layer looks like this. So inside that there is a portion of a neural network. Okay, so here are some neurons, like this is your feed forward neural network. Some non-linearity is added. Then again a feed forward up project, and you get it. The beauty is that the input to this is, imagine it's a d-dimensional input that you get. Then there is a neural network. So it's a feed forward neural network structure here. Okay. And you reach to a smaller dimensional called M. So from d dimensional you go to m directional, and you go such a down, like your m dimensional is super smaller than the input that you get as in d. Okay, it's a funnel like a structure. You start with a d, you go down to m dimensional. Okay, these are feed forward neural networks, and then you add some non-linearity. Again from m you start upwards, and then eventually you end up with a d-dimensional as an output. Okay, so for LLM architecture, for rest part of this transformer architecture, they are not even aware of this adapter layer. This adapter layer is, you inserted this layer. Okay, so you're making sure that the input comes as an d and output also comes as an d, but you just playing with the numbers of that d. Okay, so rest of an architecture is unaware what you are doing, and that's why the weights on other layers in a transformer architecture are kept constant. You don't touch that. You only play with some of the w metrics that you have in your this feed forward neural networks. You only train those smaller w matrices. So how the process goes: you give your input what you want, you got your output, the target output that you want to get from ground truth. So this is your prediction. From a ground truth, you know what the answer that you want. You calculate the cost, and then you perform back propagation. This back propagation is done only on the weight matrix w. Okay, so just by changing few w's, eventually you get to learn that your y predicted is almost similar to the actual y that you want, not for one but for all samples starting from I is equal to 1 to n in your data set. Typical neural network training philosophy comes into the picture. The only thing is, you don't train the entire LLM architecture, you only play with the weight matrices of this. Does it work? Yes, it works like a charm, and that's what it is showing you. Like the fine tuning on a, this is partial fine tuning. If you want to do it, like 100 million parameters you have to change, and if you do adapter tuning, just 150K parameters, right? So the performance with 0.15 of the parameter, isn't it great? So instead of, or llama 2, instead of 70 billion parameters, you are saying that I'm just taking 0.15% of that, and I can still achieve the same level of an accuracy that I'm getting. So the purpose is solved. Isn't it great? Yeah. So now people are getting greedy and greedy. So this is one way of fine tuning your LLM by inserting some adapter layers into it. The another method is called as a prompt tuning. So in a prompt tuning, what you do is you keep the architecture of LLM constant. You don't change this architecture, but you change what is going inside the LLM. And this is super crazy. Like when I first learned this, it was very hard to believe. So what they're saying, this is an input that goes to an LLM. This is an input that goes to an LLM, and you get the output coming out of it, and you get an output. So what they say is, along with this input, you add a new trainable numbers here, like preamble, sub prefix, and these are some numbers. Initially, like treat them as a W, some weights, some numbers. So these W's are not trained. So along with this, it goes to this LLM. So initially they are random. So the process is something like this. So this prompt is what they are actually tunable additional tokens. So this is your input embedding. This input embedding, this is a new thing that you added. Those are just some random tokens that you add. So initially those are random. So this random plus input embedding goes to an LLM. It produces an output y dash, which is not good that you wanted. So you calculated the cost. You come back and you only change the green portion of this. You perform this back propagation, change this green portion, do it again and again and again and again. Eventually, you will see that you got the best tokens as a green part, so that now your y is very close to y dash. That's how the process is. Isn't it great? It's hard to believe, but if you see actually their publication, they're saying that uh, you know you're you actually achieve with the numbers, and with a very few parameters you achieve the same level of accuracy that you want to do. Moving the next technique, that techniques is called as a parameter. So if you see in adapter tuning we inserted a new layer. So it was model level tuning. In prompt tuning, we kept architecture constant, but we added new tokens to an existing input. So that's why it's called like a prompt level. Now this is parameter tuning. So you don't change an architecture, you don't change the prompt, but you actually play with the metrics. You actually play with the weights of that architecture. Okay, and this technique is called as a LoRa, and this LoRa technique is, I think, yeah, it is from a Microsoft research, and amazing thing. Like I see, they provide huge reduction in number of parameters to be trained. The concept is really nice. What they say is, suppose W are your train weights. W are the train weights of your LLM. They say that I'll not change this W. I'll just saying that this W will be changed by some delta W. So small change I'll do to an existing LLM. And I'll keep this W constant, and this delta W is what I'll learn. Okay. And that's what you're seeing here. So if you see this W0 of X is your input, right? So normally how we say that Y output is W times X. This is a very basic linear algebra that we learned in the first course of machine learning. If X is my input vector, W is my met matrix, and Y is my output. So what they're saying is this W will be split into W0, that is train W plus delta W. This delta W is what I want to learn. So from this X with a d-dimensional input, from here you get an output as W0 dot product with X, and here you get delta W dot product with X, right? So this W0, this W0, this delta W is represented by this. Now this weight matrix has been split into, two low rank matrices. So the deliberately they're designed in such a way that, this matrix A and B, these are low rank matrix. So you have to learn very less numbers. Rest all are zeros to this matrix. So very few W's inside this matrix that you have to learn. So the back propagation happens only on the values into this low rank matrices B and A. And that's why if you see the performance of this, uh, if you see this on x-axis, you have total trainable parameters that are required. And see this is your actual, full fine-tuned model. And this is your LoRa model, the kind of results that you want. So if you see this, how much is a reduction in total number of parameters compared to full fine-tuning? 10,000x%. 10,000x times the reduction that you get in a total number of parameters that you want. And that's why it is, kind of a super popular technique. And there are so many variants of a LoRa, and it's an ongoing research. But it's an amazing innovation came from Microsoft research. So with that, we will come to an end. I'll come back to this slide again, like here. So if you want to do fine tuning is done by three ways. One way is called as a supervised fine tuning. Another way is called as a reinforcement learning with human feedback. And third is called as a distilled step by step. So we have just finished supervised fine tuning, and now we'll come to the another technique called reinforcement learning with human feedback. Now, this is a very interesting technique, and I'm sure it has a huge potential because it is designed in a way that how the end users of your LLM system gonna perceive the outcomes of this. Okay, reinforcement learning with human feedback. So if you remember, like, the fundamentals of reinforcement learning, the very popular example people give when they teach reinforcement learning is the game of a chess. Like, you can't have everything as a rule base, like no matter how my opponent is playing, I'm gonna make my next move like this and all that stuff, right? You don't do that. So in a reinforcement learning, there is an agent, and that agent, now don't confuse that this agent with an agentic RAG that we discussed. Agent is someone who interacts with an environment, who makes a move. So in a game of a chess, this agent is a player, okay, or a computer, which makes a next move as an action. So in an environment like on a chessboard, makes an action. Now the state of an environment has changed, and this agent, obviously understand what is a new state. Plus it gets the reward. If you make a good move, you will get a reward. So that reward has to be defined, because the agent need to know that what is my reward. So in game of chess, the reward is getting opponent's pieces, or getting from one side of a board to the next side, or make sure that every pawn that you have will become a queen or some other stuff there, right? So it's always something like you make an action, you get a reward. If you make a good action, you get a better reward. If you create a bad action, you get a punishment. And every action changes the states of an environment. This is how typical reinforcement learning philosophy is considered. How this reinforcement learning philosophy is used in an LLM for fine tuning. And this concept is called as a reinforcement learning with human feedback. And why it is so popular is that, LLMs are really complex because these are generative models. And for example, if you are working on a summarization task, if LLM is generating summary, Bhushan may say that, this summary is good, but someone else will say that I don't like it, though it's a generative, right? So there has to be a way by which we get some feedback from an end user. So who are your end customers? Their feedback is very important. So you take their feedback, and based on their feedback, you tune your LLM, making sure that the output generated by your LLM is appreciated well by your end customer. And that's why it's a concept called reinforcement learning with human feedback. It's called RLHF. Very popular and very interesting philosophy of training an LLM. So this RLHF is, this process has 3 steps. So the step 1 is called as an creating of the preference data set. And let's see step by step. Create a preference data set means what? This is a base model. This is the LLM which you want to fine tune. Okay. What you do is, from that base model, you create a preference data set. For example, if you are working on summarization, so what is your prompt? Summarizing the below text. I want to start gardening, but blah blah blah. So this is an input given, and then you generated a summary one. Show that summary one to your end user and ask them like how much score that you will give. So your end user say that, okay, for me the score is, I like it 70%. Then you change the prompt from summary 2, they say that the score is 0.2. You change the prompt, summary 3, the score is 0.1, and all that stuff. So what you do is, you have a different pair of inputs and output, and ask like which one your end users are actually liking it, and note down those results. And we call it as a creation of a preference data set. So you have an input, you have an output, plus you have a human feedback on that. You capture that trio. Like when I gave this input, the output generated was this, and people are liking it or not liking it. The score are very important. Okay. So this is a first step in reinforcement learning with human feedback. The second step is called as a use preference dataset to train a reward model. So we are at a step number 2. So what you do is, you actually train a new reward model. Training a new reward model means, now if you see this is actually, if you have done a machine learning course, this is actually a regression model. Yes or no? Because from a preference dataset, you know the scores. Now you create a reward model, given a prompt and an output summary. You want to predict whether your end users will like it or not. You actually predict the score. So you train a new model based on an input and output of that, and predict that score. The scores could be like 0.7, 0.3, 0.2, whatever it is. So it's a regression model. You want to minimize the reward model loss function, right? So this is a new model. So this could be a machine learning model. This could be another LLM, or like sky is the limit. Like it could be rule based. I don't know. So this rule, what this reward model will do is, this will give you a reward. Like for a given prompt, if you generate a summary, it will tell you whether this summary is good or not based on the preference data set that you created in the previous step. Step number 1, capture human feedback, create preference data set. Step number 2, use that preference data set to train a new model, and that new model is called as a reward model. Now let's go to the third step, called as a use reward model in a reinforcement learning philosophy. So this is a step number 3, where we will use the trained reward model to actually change it. So who is an agent? Agent is my base LLM, the LLM that I want to train. So what will happen? This LLM will first, given a prompt, will generate a summary. So this is an action. Like your base model generated the summary given the prompt. Now this prompt and summary goes to the reward model. This reward model will generate a score. Now if the score is not good, what you do is you change the weights of this base model. You make some small tweaks, like if this is a W, you make it W plus delta W. I'm just giving an example. There are different policies of weight updates, but we don't have much time to go details, but just for sake of simplicity, understand that you just make small changes to that. Now because you made some small changes, given a prompt, now your summary will change. Now this prompt and summary you give back to your reward model and predict the score. You do it for so many examples, making sure that you repeat this loop till the time for all the input you're saying that my scores are good, means this LLM is now trained. Now this LLM is now trained based on the human feedback, and now all the outcomes that are coming, humans are liking it, the end users of your systems are loving it. And that's a process called reinforcement learning with human feedback. Very popular technique. So how it goes, you start, you create some data set first, input and output given to the base model. This will generate a prompt and generated summary. You get a reward model. Reward model will give you the score. Based on this score, you use some model update strategies, change the base model, repeat this from all the data set till you get the baseline models. I hope this is super intuitive and you got an idea of how RLHF work. The third philosophy that is used to train fine tune an LLM is called as a distill step by step. Now this is kind of a very new technique, and I think there are most of the audience in this sessions are teachers, and you will love this philosophy. Okay, this distill step by step 2023 publication, again coming from Google Cloud AI research, and this philosophy is based on the teacher student kind of an philosophy. Okay, so you learn from a teacher and then the students perform better. Okay, now just try to relate. So from this paper, this diagram has been taken, and you can see that there are different model sizes, right? Now this is amazing. Now try to fit yourself into this diagram. Suppose you are doing your research, right? So the first problem that you will encounter is having the training data to do that, right? So from where I can get the training data? So one of the researcher may start with a large language model of this. So bigger circle means bigger model size. So if you have a very big model, but you have not enough training data, so size of a training data is this one, S1, which is very small, then this is an accuracy that you will get. On other side, even if your training data size is really high, say S3, even if you have humongous amount of training data, but the model that you have used is really small because of some reason you cannot afford to use really big model, and if you want to train it locally, that could be a reason. What is saying that even if you have lot of training data with you, but if you start with a smaller model, eventually you're not going to beat this large model. That's what they are saying. Okay, but there is a in between step. Now there is a midway where you can see that okay, I can give you some X2, some mid-size training data, and you can still use a smaller model, and then you can defeat all of them and get the better accuracy. Okay, so this is the best out of the two, like still using smaller models, still using little bit more data, and then defeating both the use cases. Okay, let's understand how it is done. So this distill step by step, as I mentioned, um, it's a teacher student kind of an philosophy. At a high level, I try to explain this stuff. So this is your teacher model, a larger model, because this is like teacher has seen a lot of a teacher has a lot of experience, they have seen a lot of data and all that stuff. Obviously teacher knows much more than the students. Okay, so what they propose is, instead of asking direct answer to the teacher, okay, what you do is you ask teacher to explain the answer. Okay, so what they're saying is, suppose the question is, Luke scored 84 points after playing 2 rounds of trivia game. If he gained the same number of points in each round, how many points did he score per round? Now if you ask this question to the teacher, teacher can directly give you an answer 84 by 2. But what you do is, instead of asking answer to the teacher, what you can do is you can leverage the experience, expertise of the teacher, and you can say that, teacher, can you explain the rationale behind this? Teacher, could you explain me how you got this answer? The teacher would be very happy. Like nowadays getting those kind of students is a little bit hard, but let's say if student comes and asks like, teacher, could you explain me how you got this answer? Then teacher is very happy to explain, like, hey, Luke scored 84 points over, so he scored 84 point in 2 rounds, means 84 by 2 is 42, that's why I got this answer as in 42. So what you do is you ask those questions, get rationale from teacher, and then do this. Now what you do is, now next time when you are training a smaller model, you know you train the smaller model not only to give the answer but also the rationale for the answer. So you force the student not to give only answer, but force the student to learn the rationale also, right? And normally you don't get the rationale by this rationale of getting an answer will come from the teacher's experience. That's what they claim. And now, that's how this distill step by step process goes, and that's how, by using smaller model but learning from a teacher, you can achieve the best scores. So that's a at a high level distill step by step for you. Now, doing this fine tuning and LLM is not something that is very complex stuff for you. Like, it's too simple. Like, I can quickly show you one of an example on a Google Cloud platform, but you can use any other platforms also. Like, it's just I'm just showing you how simple the things are. It's a matter of creating data sets. So, for example, if you can go to Vertex AI on Google Cloud platform, and there is a tab called model garden, where you'll come to know that what are different models that are available. So these are the foundation models. Now I think you are very familiar with the term called foundation models. So you have this Gemini 1.4. These are the models developed by Google. These are the models which are developed by the Google partners. And then there is a tab called fine tunable models. So there are many fine tunable models that you can get. Some of an image gen model, fades, synthesizers, and a lot of options are there. So we can go from here and you can see that, hey, I want to fine tune a Gemini model. You can click on that, and you can click saying that I want to fine tune this. So I can either, you can do it in a notebook, or you can actually click on saying that fine tune this model. So it is saying that this particular model is good for you for classification task, summarization task, question answering, chat, and all that stuff, right? So if your task belong to this, so you start with a foundation Gemini model, and then you say that this is my, say, test model maybe, and which version of Gemini that you want to do. It's Gemini 1.5, whatever that you want to go. And if you go to an advanced option based on the platform that you are using, see here it is asking like number of epochs, how many times you want to play. And if you see this is parameter efficient fine tuning, and it is asking you what is the adapter size that you want to add. Hope you remember this is an adapter tuning that we're gonna do. So just do this, select whatever the adapter size you want, click on continue. And then this is a step where you want to give a training data set. So you just need to upload a training data set. And if it is a classification problem, you have to have a question answer, like input and class input. And so type of the problem that you are showing, you will create, just upload a training file, maybe 50 to 200 examples on that. And once you provide this JSON file, just click a button called start tuning, and your tuning process gets started. Okay. So not so difficult in terms of doing the code. The difficult is choosing the right method, creating a data set, and then evaluating your models and doing that stuff. Coming back to the slides. So as you can see, the doing the fine tuning is not something really difficult, but when to do what is very important. So this is the one diagram that I personally really liked it, and I would like to share this uh, style of working, and then you can take this call. So everyone in this class, I would recommend you to start here. So prompt engineering. So do not underestimate the power of this prompt engineering. Like in our ML days, when we used to get wrong answer from a model, we used to say that the model is not good. But in case of LLM, if you're not getting right answer, probably you have not asked the right question. Okay, that's how the things have changed, right? So do some prompt engineering, try some very known techniques and all that, and then evaluate, and then see. So decide to continue or stop. In many of the cases, like 80% of the problem, if you use a strong baseline model, a good prompt engineering can give you almost all, will solve all your results, right? If after spending enough time on prompt engineering or the prompt optimizer techniques that we discuss in the part 1 of this series, if you feel that no, just prompt engineering is not working out, then you can move towards an in context learning or few shot learning, right? So few shot learning, I have already discussed with you. In your question also include some examples, like if I give you this input, my expected output is this. If my input is this, my expected output is this. And then perform this stuff. So this is called few shot learning. Then you evaluate. So most of you who are remaining, they'll see that their results are amazing after doing few shot learning. If that is also not doing, then try to do RAG and learn an example from a RAG. If that is also not working out, then come to SFT. SFT stands for supervised fine tuning. Supervised fine tuning can be done by three ways. One is, as we discussed, you can do PEFT. You can do PEFT, and PFT can be done as adapter tuning or parameter tuning, prompt tuning, or parameter tuning, right? Model tuning, model parameter tuning. Or you can do human feedback, RLHF, reinforcement learning with human feedback, or you can do distill step by step and then come to an evaluate. And I hope you achieve the best results by this task. So that's how the overall flow. You can see that the complexity and data availability increases as you go from left to right. For prompt engineering, no data is required. For few shot learning, you need to give some examples, but for supervised fine tuning, you have to have enough curated, labeled data set, and that to a quality data set. Okay, so that's it from my side today. These are my coordinates. Text me your queries or write me an email. I'll definitely try to answer the query that you have. Hope you like the session. I'm happy to get feedback from you. Thank you so much.
Thank
Any
you, sir.
questions? Any questions?
Participants can unmute themselves.
Good evening, sir.
Good evening.
Sir, can these PPTs will be available as a reference for us, like later on?
I'm really sorry. I have some restriction on sharing these PPTs. So, but I can share you some reference reference material to read. If you email me, I can share you. Definitely.
Sure, sir. Sure. So, like, do you have like the contents regarding like reinforcement learning or deep learning or generative AI, like such kind of topics or subjects? So,
Yes, definitely. Yeah. You write an email to me, I can share you the content definitely. The slides as it is, I may not be able to share, but I definitely share the references used to create those slides.
okay, sir, I do understand. Okay, sir, thank you so much. Thank you.
Thank you. Okay, if there are no questions, probably I can give 5 minutes back to the participants. Thank you so much for listening for us. It's not easy. Thank you.
Thank you, sir. Thank you, sir, for this wonderful session, sir.
Thank you. See you soon.
Hello, am I audible, Bhushan sir?
Ma'am, you're audible.
Mister? Yeah. Thank you, sir. Bhushan sir. Thank you so much for your informative session. Mister, you can go ahead with that vote of thanks. Hello. Mister sir.
Thank you, sir, for the excellent session and for making us aware about LLM fine-tuning. And thank you, participants, for attending these sessions. Also, please do mark your feedbacks. Thank you to all.
With this, we can end our session. Mister, you can end up the meeting.
Yes, ma'am.
Yeah.